Hello, I'm Mr. McBrien. This is SPH3U, the clumsy juggler, when delta dy doesn't equal 0. So we've already covered some projectile problems in previous lectures. Today, we'd like to consider cases where things are a little more complicated. It's really common to have cases where launch and landing heights are different. They're typically not put on tests because they're too long to solve. However, we're going to need this concept to calculate the range of our catapults for the catapult activity. Because our catapult doesn't launch the projectile from the floor, it launches it from a spot above the floor. So, what are we going to do today? We're going to talk about asymmetric trajectory problems. We're going to review our simple hang time and range calculations, and then we're going to adapt the same concepts to the asymmetric case, the clumsy juggler. So yesterday, we found delta t for symmetrical cases. So in our situation where we had at maximum height v2y equaling 0, of course, we had v1y equal to 9 meters per second, acceleration equal negative 9.8 meters per second squared, and we wanted to find the hang time. And we simply used our formula for acceleration in order to find the amount of time that the object took to go from release point to the apex, to the top of the parabola. And of course, if we wanted to, we could use that time to find how high up the object went before it reached the apex. And we could also use that time, if we wished, to find out how far the projectile traveled horizontally as opposed to vertically. So we can say that the time to come back down is the same as the time it took to go up. So our total hang time is 0.918 seconds times 2. And then we can use the horizontal speed of 12 meters per second to get our range, 22 meters. And of course, we also could have used the delta dy equals v1y delta t plus 1/2 a delta t squared equation as an alternative approach to get that distance. So in this case, we can simply state that that delta dy equals 0 because of the fact that we have a symmetrical parabola, and use that to set up our expression where v1y delta t plus 1/2 at squared equals 0. Factor out delta t and get either delta t equals 0 or v1y plus 1/2 a delta t equals 0. And from this, we can say the delta t equals 0 case, where we release the object and it's at the height of release, is a trivial case, and solve for v1, solve for the other case, solve for delta t, since we know delta t isn't equal to 0. And we get the exact same answer, no great surprise. We get 1.837 seconds versus the other way we solved the problem. Using that 1.837 seconds, the rest of the math is the exact same to calculate the range. But what do we do if we can't set delta d equal to 0? We can't multiply the time to the summit by 2, and we can't set that expression equal to 0. And there's lots of examples of this kind of thing. For example, a baseball is thrown from a pitcher's mound down to a catcher's glove that's almost 2 meters below the release point. A juggler throws a ball up from height 1 meter where he released it, and it fell to the floor because he didn't catch it. Or a cannon fires from a castle wall at an angle 15 degrees above horizontal, and the cannonball hits the ground 12 meters below. All of these are cases of asymmetric trajectories. So the impact isn't at the same height as the release, and so delta D is not equal to 0. So we can, if we want to, we can still do our calculation. The juggler throws the ball up at 2 meters per second. We want to find out how long until it hits the floor. We can figure out the time to the apex, and that's simply our case of using the acceleration to get v2. We know v2 equals 0. We know v1 equals 2 meters per second. We can calculate the time it'll take to get to the apex. That's not a problem. The problem is that it won't take the same amount of time to get to the floor because the distance is different. So how do we solve this? Well, we go back to our expression for displacement. Delta dy equals v1y delta t plus 1/2 a delta t squared. But this time, we can't set it equal to 0. So here the problem's laid out for us. Our delta d is equal to -1 meters. So 1 meter below our release point. v1 is 2 meters per second, so 2 meters per second up. The acceleration is -9.8 straight down, and our problem is find delta t. So we can substitute in -1 meters per second equals, and this should be -1 meters, equals 2 meters per second times delta t plus 1/2 -9.8 meters per second squared delta t squared. And we can go through and move the -1 term across to the other side. And maybe for tidiness, multiply through by -1 to get 4.9 meters per second squared times delta t squared minus 2 meters per second delta t minus 1 meter equals 0. And this, perhaps unfortunately, we need to use the quadratic formula to solve. So here's our familiar quadratic formula. Delta t equals -b plus or minus root b squared minus 4ac over 2a. And this is really not that bad. So if we substitute in, we get 2 plus or minus -2 squared minus 4 times 4.9 times -1 over 2 times 4.9. And we get an interesting answer. We get a negative number, -0.292 seconds, ignoring significant figures, -0.292 seconds, or 0.7 seconds. So does this answer make sense? Well, we know that it took 0.2 seconds to get to the apex and another 0.2 to get back down to the hand that missed it. And so we're saying it took 0.3 seconds to get from passing that hand down to the ground. That doesn't sound that bad. And the -0.292 case, we're saying that if the trajectory were extrapolated out to negative time, it would have gone from the floor up to the hand, up to the 1 meter point in 0.292 seconds. And that sounds reasonable too. So this does seem like a reasonable result. Okay, so now we know that the ball is going to hit at time 0.700 seconds. If we wanted to, and we had v1x, which is vx, we could calculate how far from the juggler's hand the ball would land in the x direction. We could also do things like calculate the speed that the ball would hit the ground at, and things like the angle it would hit at, the impact angle. So really, we have a new tool then. The quadratic formula isn't really all that bad for doing that calculation and gives us a lot of insight into the motion of the projectile. And we've already worked through this homework previously, so I think we can end here. Hopefully this is useful in getting your catapult lab put together. Thanks for your time and have a great night.